So we've already talked a little bit about inverses this year when we talked about sine inverse and cosine inverse. So an inverse of a function, one of the ways we normally describe that is switching x and y. So we can see that it says that right here. If a function f has all these ordered pairs x, y, then the inverse of f would be all of the points y, x with them switched. So the inverse of this first function right here would just be 2, 1, 4, 6, 3, negative 1. We can skip the second one. You guys know how to switch two numbers. What an inverse also, the way we can also see it on a graph is a reflection over the line y equals x. So I'll color code this here just so you can see it, but if this is f of x, this would be f inverse of x. Because here's the line y equals x. I'm just going to write that down a little bit. And you can think about the relationship between those two things, like switching x and y and reflecting over the line y equals x. Basically what we're saying here is, what if y equaled x and vice versa? Meaning like we're switching them. Another way to think about an inverse function is it's sort of the opposite of a function. It's the opposite operation of a function. We could say that it undoes a function. Is it undoes a word? Surely it is. Maybe not. So a really, really simple example would be like if f of x is x plus 5, the inverse of that would be x minus 5. You've got a function that's always adding 5 to a number. The opposite of that would be subtracting 5 from the number. And so if we thought about both of these things like one function after the other, if we had like, if we used x equals 2, 2 plus 5 is 7, 7 minus 5 is 2. It kind of brings us back to what we started. It just undoes what we just did. Turn to your neighbor. What is the sign of sine inverse of negative root 3 over 2? Do it step by step. All right, so when we do sine inverse of negative root 3 over 2, what angle does that give us? Yeah. And so if we take the sine of negative pi over 3, what is the y coordinate of that angle? negative root 3 over 2. So notice how sine and sine inverse have undone each other. They basically canceled out. We started with negative root 3 over 2. We ended up with negative root 3 over 2. Now, because of like the restrictions on the circle, this won't always happen. They don't always cancel each other out. But that's the basic idea, is that you're doing one thing and then you're kind of just undoing that operation. To review a little bit about what you talked about in Algebra 2, the inverse of a function is a function if and only if the original function passes the horizontal line test. And if the inverse of a function is a function, then the original function is called one-to-one. So for example, number 5 here, the inverse is a function because it passes the horizontal line test. The inverse would be our cube root of x function here. Whoa, that looks terrible. Kind of look like that. That is the function. But the inverse of x squared is not a function because we would get this sideways parabola here, and that would fail the vertical line test. And we can see that because the original function fails the horizontal line test. And sometimes this matters and sometimes it doesn't. It sort of depends on the context of the problem. We'll see some examples of that today. So, throw back here to find the inverse of a function. You can rewrite it as y equals instead of f of x equals. You're going to switch x and y and then solve for y. And then rewrite it as f inverse of x. Alternatively, you could solve for x first, and then switch x and y afterwards. It doesn't matter. This process that we're doing is undoing a function. So for letter A here, we have y equals 8x minus 3. So if we switch x and y, and then we solve for y, we're just undoing all the operations in the reverse order of operations here. So we add 3 to both sides, and then we divide by 8. You guys do letter B. All right, so we square both sides to get rid of the square root. We subtract 5. We divide by 2. Oh. Actually, these are not quite inverses. We didn't do anything wrong with our algebra, but something else is going on here. Turn to your neighbor, talk about it. Why am I saying they're not quite inverses? Oh, what you got?
Either it's undefined when plugging into a graph or it fails the vertical line check.
Okay. Yeah, anyone want to elaborate on that or add to it? Or other thoughts? Okay, in general, yes. Here's square root of 2x plus 5. Let's see, we need x squared minus 5 over 2. Would we say that those functions are a reflection of each other over the line y equals x? No. The square root function is basically half of a parabola sideways, whereas x squared minus 5 over 2 is a full parabola. Actually, I don't know if I can do this on here. Can I do this? X greater than 0. Yeah. I'm not that good with Desmos yet. So what we need to do basically for these functions to actually be inverses of each other, since we started with the red curve right there, we need exactly half of this blue curve. You can see right here where the red meets the x-axis, like that's basically the vertex of this parabola. And so we just have this part. So the part of the parabola that we want is just this part, from x equals 0 to infinity. So we just want the positive half of that parabola. And so what we are going to do here is we're going to say with domain 0 to infinity. Because then it's going to look like that. And the way to know that without looking at the graph is the domain of the inverse matches the range of the original. The domain and range are switching because we're switching x and y. So the domain of the original becomes the range of the inverse and vice versa. We can know the range of the original because this is a function that is just shifted left. And there's a vertical stretch to it, the 2 right there. Or it's a horizontal stretch actually. But it's not shifting up or down, which means our range is from 0 to infinity. Our next class is actually going to be reviewing all the parent graphs. Is that right? Yes, our next class. Because on Friday we won't really have class because Friday's junior focus day, so like more than half of you guys are going to be doing that instead. So our next class is going to be next week. So we're going to review all of our parent graphs. But we want to remember this is just a left shift. It's not a vertical shift at all. Okay. So the other thing that we're doing with inverses is we're going to be proving whether two functions are inverse functions of each other. The words that we're going to see are prove. We might see the words use composition, prove algebraically. But our process here is we're gonna use composition of functions, and we're gonna look and see if f of g of x equals x and g of f of x equals x. Basically, what we're looking to see is do these functions cancel each other out? Or do they undo each other? It's kind of the same thing we did with sine inverse. Like we plugged in negative root 3 over 2 and we got that as a result. The functions cancel each other out. So if we get x, just x left over after we do composition, then that means they're inverses of each other. So, and we have to do both. We have to do f of g of x and g of f of x. And it'll normally be pretty nice and satisfying when they are inverses of each other because everything will just cancel. So when we do f of g of x, we distribute, we get x plus 6 minus 6, and then we see that those cancel. If f of g of x equals x, like the other one is going to work too, but we do have to do both. That's part of the proof. You guys go ahead and do it. You should get x. All right, did you guys get this to equal x? Distribute the 1/2, x minus 3 plus 3, that equals x. Yes. G of x and f of x are inverses. Okay. Are these functions inverses in number 7? Let's actually just skip the algebraically. Algebraically is what we just did. Notice how it doesn't say explain, it doesn't say prove graphically because we actually can't prove it graphically, but we can explain it graphically. Turn to your neighbor. Are these function inverses? How can we tell from the graph? All right, so are they inverses of each other? C? Oh no. C. How can we see that on the graph? Ooh. How can we tell? Yeah.
The x and y's are like opposite, like the x-intercept is at -5 and the y-intercept is at -5, so it's like 0, -5, -5, 0.
Okay, yeah, yeah. So you're seeing the opposite x's and y's? Yep. What's another thing that we can see on this graph here? Okay, what's the number one thing we want to look for on a graph to see if things are inverses of each other? Yes, reflection over what?
The y from x line.
Yes. Oops. So our reflections over the line y equals x. We're gonna skip this one for now here. So, when we're finding an inverse here of a rational function, this can be a little bit challenging algebraically, but I'm going to show you guys how to do it, and then we'll get a chance to do some examples in a little bit. So, first, we're going to rewrite it as y equals, and then we're going to switch x and y. And I actually want to give you guys a minute to discuss with your neighbor. How would you solve this for y? What would your next steps be? How would that work out? See if you're right. All right, let's go over it. So, first step, what do we think? Anna, what was your first step? Anna Glassman.
Oh, multiplying y.
Yes, that's the correct first step. You gotta get y off the bottom. And then you also combined it. What did you do at the same time there?
Oh yeah, I combined it to like I just multiplied it, so it's like yx plus 3x.
Yeah. Yeah, so you can do that all in one step where you multiply and distribute. Okay, did you know what to do next?
And then I moved everything to the left.
Okay, everything?
Yeah.
Okay, that's a good idea, but not what we want to do. We want to do something else. Any ideas?
Oh wait, do you just move the 6 and then factor out?
No. Close. We are going to move some stuff to some side and some stuff to the others. This is actually the same process that we did back in the day. This might give you guys PTSD. But like 3 to the x minus 2 equals 4 to the 2x plus 1. We natural logged both sides and brought that out, and we distributed. It's the same algebra that we're doing here. After we distributed, our goal was to get all of the x's to one side. Our goal right now is similar. We're going to get all the y's to one side because we're trying to solve for y. So that means we're going to have yx minus y equals 6 minus 3x. So what I'm doing there is I'm subtracting 3x from both sides, and I'm subtracting y from both sides. And the goal is to get the y's on one side. And do we know what the next step would be?
Divide by x.
No, can't divide by x because we would have to divide both things by x. Yes. Factor out y. So we'd have y parentheses x, what? Minus 1, yeah. And then our very last step would be
Move the x minus 1 to the other side.
yes, using what operation? Division, yes. Yes. Okay, so that's how you do those. Sweet. Our last example here, number 10, we're going to do prove algebraically. And we're going to use composition of functions to determine if they're inverses. Is there a difference between those two phrases in terms of what we have to do? No, so this is actually redundant, so we can just cross one of those out. We don't need it. I don't know why it's printed twice. Hopefully these are, otherwise it's going to be not that satisfying. But this is similar to the composition that we did in our warm-up. So we'll do f of g of x together, and then you guys will do the other one. So 2x plus 4 plus 4. Oops, nope. Not like that. 2x plus 4 over x minus 1 plus 4. 2x plus 4 over x minus 1 minus 2. What's our next step going to be?
For the GCF.
The C is right.
Lowest common denominator.
Yes. Common denominator. Once we find a common denominator, what are we going to do? After the common denominator, what do we do?
Distribute.
I like to do it before distributing. What's the common denominator allow us to do? Cancel. Yes. Cancel all the denominators. The reason I like to cancel first before distributing is often students will distribute incorrectly. What I see a lot is distributing the 4 to the top and the bottom. That would be wrong. You need to just distribute it to the top. So that's why I like to cancel first, kind of just avoid that common pitfall. So this becomes 2x plus 4 plus 4x minus 4. And over 2x plus 4 minus 2x plus 2. And so we get 6x over 6, which equals x. Nice. That means g of f of x should also equal x. But I want you guys to find it. You can use this space down here. It should. If it doesn't equal x, then it just means you made a mistake somewhere. And so you just have to go back and find it. So we get our common denominator. Cancel. 2x plus 8 plus 4x minus 8. X plus 4 minus x plus 2. I'm breaking my own rule there. I'm distributing while I'm doing it, but that's because I'm just checking it here. We get 6x over 6 again. It won't always work out like that, where you get the same like second to last step, but sometimes it will. We just want to say here, yes, f of x and g of x are inverses of each other. You can say therefore. Yeah, I like the therefore instead of saying yes. Therefore, f of x and g of x are inverses of each other. In calculus, especially AP calculus, we have to write like little sentences like that to kind of sum up what we're saying, but also in applied calculus as well. So start just thinking about that. Especially because we're doing a proof, we have to have some kind of conclusion to what we're saying. Okay, so there's a couple other examples on there that we didn't get to that I can just leave for you guys as extra practice.